Hello everyone, welcome to the signal system class. In this presentation, we are going to derive the jet transform of impulse function. We know that an impulse function is denoted by delta t, but here we are going to consider it as delta n, that means discrete impulse function, because whenever we are asked to find out what is the jet transform of an impulse function, that is obviously a discrete impulse function, because we are not going to apply jet transform for a continuous signal. So, if we are asked to find out the jet transform of an impulse function, that is definitely for discrete impulse function only. Now, we know that a discrete impulse function is denoted by delta n, that is, if an impulse function is denoted in t domain by delta t, then we will represent the discrete function by delta n, and it can be defined as delta n will be equal to 1 when n is equal to 0, and delta n is equal to 0 when n is not equal to 0. And the graph of the discrete impulse will be as shown in this figure. That is, the value of this delta n will exist only at n is equal to 0, and its value will be equal to 1 if it is a unit impulse function. Now, at n equal to 0, we find that this is an impulse whose amplitude is 1, and in all other cases the value of this delta n is equal to 0. That is, at n is equal to 1, n is equal to 2, n is equal to 3, n is equal to minus 1, n is equal to minus 2. At all the other values, this value is going to be, the value of delta n is going to be 0. So, always a discrete impulse function is going to have value only at n is equal to 0, and the value of del n at n is equal to 0 will be equal to 1. Now, the problem is that we have to find out the jet transform of the impulse function. Now, we know that the jet transform of any signal xn is given by this formula, that is, jet transform of a function xn is equal to summation n is equal to minus infinity to plus infinity of xn into z to the power minus n. And we know that the value of the function is delta n, so we will find out the jet transform of delta n. So, jet transform of delta n will be equal to n is equal to minus infinity to plus infinity. We have substituted the value of xn is equal to delta n into z to the power minus n. So, we will, in this equation we will substitute the different values of n. So, we will get the values as, if we substitute the different values of n, we will get the values as del of minus 2 into z to the power 2 plus del of minus 1 into z to the power 1 plus del of 0 into z to the power minus 0 plus del of 1 into z to the power minus 1, and so on. Like this side also, and similarly this side also we will get the values. Now, we see here that the value of delta exists only at 0, that is del of 0. So, the value of del of minus 2 will be equal to 0. So, this term will be 0. Similarly, the value of delta of minus 1 will also be 0, so that this term will also be 0. Similarly, this term will also be 0, and del of 0, that is, since this function exists only at n is equal to 0, so this value will be equal to 1. So, we find that the jet transform of the discrete impulse is equal to 1, that is, jet transform of impulse function is equal to 1. So, we find that the jet transform of an impulse function is equal to 1. So, if we have to find out the transform of impulse function, then it is always going to be 1. any transform of the impulse function is always equal to 1. That is, the Laplace transform of the impulse function delta t is also equal to 1. The Fourier transform of the impulse function delta t is also equal to 1. The discrete Fourier transform of delta of n is also equal to 1, and the jet transform of the impulse function delta n is always equal to 1. So, this is how we can find out the jet transform of an impulse function. This is all for this presentation. See you in the next presentation.